What's cracking, guys? In this video I'm covering perceiver, general perception with iterative attention, and at the end of the video I'm gonna contrast it with the newly published perceiver IO paper. It's a work by DeepMind team, Andrew Jegal, Felix Gimeno, Andrew Bruck, Andrew Tisserman, Oriol Vinhals, and João Carreira. So the idea is to generate this general perception architecture and make it modality agnostic, and I'm gonna break that down in a little bit, but let's see the motivation behind the paper. So the perception models used in deep learning are designed for individual modalities, often relying on domain-specific assumptions such as the local grid structures, and I guess they're referring to CNN here, but basically depending on which modality you're using in your deep learning pipeline, if you have like an image, or if you have an audio, or if you have like a point cloud, you're going to use heavily specialized architectures to kind of process and understand all of those modalities. The whole idea of this paper is to kind of ditch all of those specific priors, which are modality dependent. Like, for example, when you're using a CNN, you're basically exploiting the fact that neighboring pixels, their intensities are correlated, and so you can use a kernel that's like 3x3, and you can kind of shift it and share the weights, whereby you're also exploiting the fact that the statistics will not change across the image. And so they say it here nicely. In this paper, we introduced the perceiver, a model that builds upon transformers and hence makes few architectural assumptions about the relationship between its inputs, but it also scales to hundreds of thousands of inputs like ComNets. So on the one hand, they're reusing transformers, which are like proven to be very good at modeling arbitrary relationships between the inputs, and on the other hand, they kind of avoided this quadratic complexity problem that transformers have, and we're going to see how they did it. And that's what enables them to apply this model to hundreds of thousands of inputs. So let's dig into the architecture straight away. Here it is. It basically, as you can see here, we have this latent array, which is n times d dimensions. We have this byte array, which is basically your input modality. So this thing here is going to be either your image or your audio or your video or whatnot. So whatever you have. So let me kind of explain that using this image below. Here you can see various modalities. We have like image here. We have like a video. They kind of sampled a couple of frames from the video. They have the audio here that's aligned with this video, and we have a point cloud here. So let me take one example and form the byte array like for this image. So this image was going to be I guess it's a ImageNet image, so it's 224 times 224, and that's like 50k pixels, okay? So basically how they're going to flatten it out and form a 50k, so that will be m, I guess. So that's the m component of the byte array, as you can see here. So we had m times c. And then the C is going to be, because this is an RGB image, it's going to be m times 3, and that's going to be, 50k times 3. And as you can see, this is like a pretty big input that transformers cannot handle by themselves. And similarly for the video, they're going to basically concatenate the features, the input features from the images as well as from the audio, and they're going to form a single m times c array again. So that's this part. Now let's see how the model works. So basically you have this latent array and you use it to form these query vectors. So this is your regular QKV attention pattern, and what you do, you form queries from this latent array and you form keys and values from your input. And so you're basically in a way questioning the input for valuable information, and then you're combining value vectors using those scores you formed using the Q and K matrices to get like a novel representation here. So this is the first component of the pipeline. You have basically this cross attention module. This is the first part. Then the second important part is once you have this vector that contains certain information from your input modality, you're then going to apply your basically the original transformer block here. You're gonna just kind of concatenate a couple of those blocks and form this latent transformer, and that's basically the second component of the pipeline. Now what I do is just kind of repeat this thing. So as you can see here, and now we form the query vectors, and we again query the keys here, and we form a novel representation here. So how you can think about this is basically the latent transformers are kind of refining the representation so that we can ask better questions to the input, ask better questions to the input modality and form more informative representations. And then at the end, we can kind of use that for whatever a specific task we're having at hand. So basically classification or not. So that's the main idea. It's fairly simple. And one detail that's worth mentioning here is that they are sharing weights between these latent transformers. So as you can see here, these dotted, this dashed line means that this latent transformer has the same weights as this one. And they're doing the same thing for the cross attention. Now there is a small and important detail, I guess. They are actually, for this cross attention, the first one is going to have its own weights, and then all of the other cross attention modules are going to share the weights, because otherwise they had some instability problems. Okay, so if you watch some of my previous videos, like I covered Facebook DETR model in one of my previous videos, and I think it's a nice comparison to contrast this perceiver with DETR model. So we could see many basic ideas and like building blocks in this DETR model. So as you can see here, so this plays a role of basically this part of the latent array. So you have this object queries. And then you have a basically transformer decoder. So that's the same thing as this latent transformer here. And as you can see here, this is, if we treat this as the byte array, this representation here, basically then we have a similar structure all in all. So obviously they've replaced this whole thing here. So instead of having the specific CNN parts, and which are obviously modality specific, and then doing this intricate stuff, they just kind of flatten out the inputs, they do the cross attention, and then they apply the transformers. But yeah, I thought it would be neat to kind of contrast that to the perceiver module. So again, if you kind of ditch this part and you just use your input directly here, and then the only other difference would be, I guess, interleaving these latent transformers to kind of refine the representations. And here they are constantly, in every single layer, they're kind of consulting the input modality. So yeah, I thought it would be neat to kind of mention this. Okay, let's continue. Let me share a couple more interesting ideas here. They mention it here. Because we optionally share weights between each instance of the transformer tower, so that's the latent transformer, and between all instances of the cross-attention module but the first, our model can be interpreted as a recurrent neural network, but unrolled in depth using the same input, so the same input rather than in time. So unrolled in depth and using the same inputs. So those are the differences. So basically, a quick a recap. We have when we have RNN, we have basically NN here. So we have our model here. We input at time step 1, whatever the modality may be here. So for example, like a textual token or something. What we do then is we unroll this. So we apply, basically the weights here are shared, and then we apply another input, so like a different token, and then we repeat this on and on. And so the difference here is, instead of using different inputs, they're using constantly the same input modality. So that's the byte array here. So let me go back here. And so secondly, they are obviously not unrolling in time, they are unrolling in depth. So we have these powerful latent transformers where we are unrolling them in depth. So I guess there is a nice mapping between these two ideas. And I guess this thing, but the first one, so this kind of asymmetry between not sharing the weights in the first cross attention module with the other ones is kind of worth further investigation. Continuing on here, second thing I want to mention here, and this is fairly important, this is what enables us to use a perceiver directly on the input modality without doing all of those tricks. Like, for example, the vision transformer had to first do one layer of convolution, or how they kind of originally called it is to take the patches and linearly project them, but you can implement that using a single convolutional layer. And only then, when you reduce the spatial dimensions, so you basically have a much less number of tokens, you can then pass them through the transformer. So in order to avoid that, we need to reduce the complexity. And here is the main reason why perceiver works. This results in an architecture with complexity m times n plus l times n squared. And this is the key. So m is the size of the input modality, and n is the size of the latent array. And they usually use something like 512 here. And if you remember, we had 50K for the RGB image from ImageNet. So there is a huge difference there, and we can save a lot of computation just here because we don't have a quadratic dependency on M. And this thing here is L is just a number of layers in the latent transformer, and N is the, again, latent dimension, and so it's N squared because we are using the transformer, but this time we're using the transformer and we're feeding as the input those latent variables instead of using the input modality. So this is how they managed to save the computation, and this is the whole trick. And so by decoupling the input size and the depth, we can add additional transformer layers at a cost that's independent of the input size. And that's cool. So we don't have M squared, we have N squared. So basically the main thing to do to reduce the complexity is to have this projection of the input modality into this latent space by doing this query KQV, basically attention, and reducing using this as a bottleneck. One final remark is, let me mention the positional encodings. So the reason we have to use position encodings is the same as the reason why we had to use the positional encodings in the original transformer in the first place. And that's because transformers are permutation, actually equivariant, not invariant. That means that if you have an input here, and if you rearrange it, so this is some tokens, and if you rearrange them, your output is going to be rearranged in the same fashion. And that's why it's equivariant, not invariant. If it was invariant, then that means however we permute the input sequence, the outputs would remain the same. And if it's equivariant, then it's kind of following the pattern of the input permutation at the output. Hopefully that's clear. So basically, they are using same Fourier features as in the original transformer paper, and they mention some small detail here. So in language modeling, transformer inputs are typically produced by adding a position encoding to the input encoding, so by adding them. And we found it beneficial to instead concatenate the position and input features before passing them into the perceiver. So this is just a minor detail, obviously, but I just wanted to mention that they have to add this, in a way, modality-specific positional encodings, but that's a minor, prior compared to having to actually tweak the architecture to deal with the modality. Okay, those are pretty much all of the details you need to know about the perceiver. Now let's see some results. They did experiments on various modalities. One of them were images. They also did on audio, on video, and on point clouds. Let's start with images. So they have results here. Let me go back here. And as you can see here, they compare the perceiver with the simplest baselines, such as ResNet 50, VAT, so the vision transformer. Here they additionally add the FF-means Fourier features. They basically concatenate the Fourier features along all of the pixels, and then they pass that through the ResNet and VAT. And so that's the second block. And finally, they have basically the original transformer. And the only thing they had to do is tweak, so resize the input image from 224 to 224 to 64 times 64, because as we know, quadratic complexity. Before I even comment the results and the drop we have here, you need to be cognizant of the next fact, and that's that these are the simplest baselines. If we took a SOTA, so the state-of-the-art model on ImageNet, with no pre-training, and those would be NF-nets and efficient nets V2, we can see that, so basically the top one accuracy is 86.5, which is way higher compared to what perceiver achieved here. And then efficient nets V2 additionally, with no pre-training, they achieve roughly this accuracy, but they're also way more efficient, obviously, both parameter-wise and computation-wise, etc. So the reason I'm mentioning this is because they are not trying to compare perceiver with the highly specialized modality-specific architectures. They're just trying to show that they are as good or even a bit better than the regular baselines. And so now let's see the results. We can see that it's obviously better than both the ResNet and the VAT, and we can see a significant drop here. So from 77 to 73, and a smaller drop for the VAT. A quick remark on this drop for ResNet 50 when we add the Fourier features. Basically, the authors mentioned here to account for the perceiver's use of features at input, we trained versions of the benchmark models with this input as well, and found that they produce comparable, if slightly worse, performance to models trained solely on RGB input. And I mean, this slightly worse is a very arguable statement because, I mean, dropping from 77 to 73, 4% in top one seems like a significant drop, and I would love to know why. And I think I would give this another look, whether there is some bug here or I don't know. It looks suspicious to me in any case. Anyways, let me show you some other interesting results. So these ones here. So I mentioned the permutation equivariance of the transformers and as well as perceiver I/O, obviously. And so they did a small experiment here to kind of further consolidate this idea of using modality-agnostic like architecture such as perceiver I/O. And the whole point is, so what it did is they took a raw image, and we have scores here. So top one accuracy, and then they did this permutation, and you can see that there is a significant drop happening here, as well as for VAT, although somewhat smaller, obviously. And here we have like same results. And let me just quickly explain what this permutation means. So what they do is they take an ImageNet image. Let me draw a simplified image. There will be 3 by 3 pixels, so something like this. 1, 2, 3, 1, 2, 3. Okay, and I'm gonna label these pixels as so 1, 2, 3, 4, 5, 6, etc., all the way until now 9. Okay, so what it did is they basically just predefined like a deterministic permutation mapping. So, for example, one possible solution would be something like this, like. I would put like 5 here, and then 1, and then like 3 or whatnot. And so what it means basically is that the transformation they do upon the input images is they'll basically shift this pixel intensity, whatever it is, to this location here. They'll shift this pixel intensity to this location here, and they do this for every single pixel according to this permutation table. And so and they also include, as you can see here, the Fourier features, because to make it a bit more fair. But like obviously, because CNNs are used to exploiting the local correlations, and now here it's kind of that kind of assumption is violated, because from a natural image here you end up with something that's obviously artificial, and so you can see a significant drop happening for the CNN architecture. VAT performs somewhat better, although there is a drop there as well. The reason is because the first layer, as I mentioned, of the VAT is basically a CNN transform, and then we have transformer blocks. So that's why we have, because of that, I guess, because of the CNN part, I guess that's why we suffer, the performance suffers here. And because these are permutation equivariant, so both the original transformer as well as the perceiver, ignoring whether the positional encodings are learned or just Fourier ones, they still kind of preserve the performance. Okay, so that was a quick remark and experiment they did, and this kind of further emphasizes the need to have these generic architectures such as perceiver. Okay, continuing on, let me show you these. They had some nice attention maps visualized here. So what you see here is basically this image here. You take the first cross-attention block from the perceiver model, and you basically take so again, you have a latent vector here. So this will be n-dimensional. And the modality is this one here. So we have m pixels here. So what they do is they take a query, so a single query. So maybe they form from this position, so from this feature vector, latent feature vector, they form a query vector. And they use that query vector to query all of the keys of this image, and that's how they form all of these visualizations, okay? So basically, these are just attention scores prior to softmax. So again, every single pixel here will have its own key vector, and we're going to do like dot product between this query and all of the keys for every pixel, and that's how we form these scores. And so you can see there is a qualitative change happening between this one and these ones. So that's the reason is because, as I mentioned, they have unique weights for this first cross-attention module, and they share the weights for all of the other modules. And they were using actually eight cross-attention modules for the ImageNet model. That means they'll be consulting the input modality, i.e. the image, 8 times, and then they'll have obviously the refinements using the latent transformers. But you can see a qualitative change between these ones, and so because these two share the same weights, whereas this has separate set of weights. And you can see obviously qualitative change. So here you can even notice a dog image, even though these are only scores. I'm fairly sure this is not overlaid on top of the image. I'm fairly sure this just pops up when you calculate these scores. And here you can see these types of 2D sinusoids, I guess, some complex 2D signals, which kind of resemble the Fourier features in a way. And so they speculate that that's because they're using Fourier features as the positional embeddings, because once they use the learned ones, they mention that they don't see these patterns anymore. So I guess it heavily correlates with the use of Fourier features. And here is just kind of like this same thing broken down for multiple query vectors. So we just saw a single query vector. Remember, there are 512 of these for the ImageNet task, and so they can have 512 of these visualizations. They just have 100 here and a couple of other ones here. I guess you can just see they correlate heavily, these ones with these ones, obviously. Continuing on to other modalities, they did a same set of experiments on this AudioSet dataset. So basically, AudioSet contains a bunch of data, and it's videos combined with audio, obviously. And they have some baselines here, and they compare perceiver with those baselines using only audio as the modality, using only video, and using both the audio and video. They basically just concatenate the data from audio and video into that M times C byte array. So the details are not that important in my opinion, but yeah, a couple of interesting facts here. So first, perceiver is kind of on pair or better compared to all of these other baselines, including ResNet 50 again. But like this CNN14, which is super specialized, has a bit higher score, and once they kind of drop domain-specific information, then they are now kind of better. I mean, you can always make your model perform better than the baselines if you do this kind of stuff. But yeah, as I mentioned previously, they're trying to compare with baselines and show that this same model, with some small tweaks like specific augmentations and specific positional encodings, they can kind of have on-pair performance with the baselines across different modalities. And that's the whole point of the paper. On video, we can see it performs better than these two baselines here. And finally, for the combination, we can see that obviously using both modalities helps boost the performance. So it's way better compared to using only video or comparing only audio or using only audio. And again, this baseline that has this specific late stage fusion has a bit better performance, but again, not that important. For me, what's interesting is that the difference between raw audio and MEL spectrogram when we're using only the audio modality is like very similar, and usually you get like a huge boost by using these spectrograms. So I guess this is something that's worth further investigation and something I found interesting. Yeah. A small rant here, they mentioned this. So for video, basically a full 32 frame clip at this resolution has more than 2 million pixels. And that's obviously not something that's feasible even with a model such as Perceiver. So they mentioned here they experimented using tiny space-time patches with dimensions 2 × 8 × 8, resulting in a total of 12,000 inputs to the perceiver. So this resembles what VAT is doing a lot, and so they were kind of comparing themselves with VAT, and here they're doing basically the same thing, a hack on how to reduce the input modality into using domain-specific knowledge into smaller modality and then input it back into perceiver. So I assume like this does not look consistent with the rest of the ideas in this paper, and yeah. Just leave your comments. What are your thoughts on this, and whether this is violating the whole idea of the perceiver model. And finally, I'm just going to end it up here, showing results on the basically point cloud classification. The goal here is given 3D point cloud to classify an object into a certain category. And again, you can see VATs, ResNets, and Transformer Perceiver outperforms all of them. But again, when you have highly specialized architecture such as this PointNet++, it's way better compared to Perceiver by at least 6 points here. I'm going to wrap up this paper with this sentence. So they mention it here: while we reduce the amount of modality-specific prior knowledge in the model, we still employ modality-specific augmentation and position encoding. And we also just saw the trick they are doing to make video modality feasible. And so this is something to have in mind. We're still definitely struggling with videos. Finally, before I contrast this paper with Perceiver IO with the novel paper, I want to mention one more thing that I saw in the ablations here. So let me just find it. So what they did here is they basically omitted, as they say here, performance of models built from a stack of cross-attention layers with no latent transformers. And now this is way more equivalent to what the DETR, Facebook DETR model is doing. And you can see that the accuracy is way lower compared to using those latent transformers to refine the representation. So this is a kind of argument behind the usage of latent transformers. Okay, now let me quickly contrast this paper with Perceiver.io. Okay, Perceiver.io, a general architecture for structured inputs and outputs. Again, the DeepMind team. And they say here, while the perceiver supports many kinds of inputs, it can only produce very simple outputs such as class scores. Perceiver.io overcomes this limitation without sacrificing the original's appealing properties by learning to flexibly query the model's latent space to produce outputs of arbitrary size and semantics. So in the original paper, all of the tasks we saw, so ImageNet, AudioSet, and those point clouds, all of those were classification tasks. And so we had a simple, like the output structure was very simple. When you have more complex problems, such as trying to make an agent for StarCraft 2, then you have much more structured output. So the output may be something like this. Like you have one array that tells you which agent you should select, so which of the characters you should select. And then once you select the agent, you have like a matrix that tells you what's the probability of moving to all of these locations. So maybe you have something like 4x4 matrix, and basically you have a probability of where the current character, the selected character, should move. And so you have like complex structured output. And the thing is, the original perceiver, even though it was very flexible with the input, it wasn't as flexible with the output. And so basically what this paper does, and they mention it here, and they say here, our main technical contribution is Perceiver.io's decoding procedure. So let's see what they mean by that. Here is the architecture. Let me just kind of contrast this one with the original perceiver paper. So this part is the same. So we have latent array n times d. We have the input byte array m times c. We just do this cross-attention module. We do the latent transformer part. So this is the latent transformer part. This is the cross-attention part. And we just repeat that part, rinse and repeat. And that's the same thing as with the original perceiver. So the novel thing here is this output query array. So what you do is, depending on your desired outputs, you have like an output array that maybe has like O vectors, and every vector has E features. So what you would do is form O query vectors, and basically again do a cross like attention logic. And so because you have O vectors here, you're gonna end up with O vectors here. Zooming in into the decoder head, because this is the main contribution of the paper. Let me kind of like break it down a little bit more. First things first, these query vectors are going to be task dependent. So depending on the structured output you want to achieve, you'll be either integrating some domain specific knowledge here, or you're going to make these learnable. Let's see how the shapes work out here. So we know we have basically O of these, and their dimensionality is not that important. It's going to be like X, and the only important thing is that they match with like key vectors, because we're going to do dot products here in order to form the attention scores. Now the important part is that the value vectors, so these here, have the dimensionality E, if that's our target, as you can see here. So E is our target, so we want to have the dimensionality of these value vectors should be E, and we need to have O of these, and that's how we make sure that this thing here is O times E, and that's our desired shape. So basically everything else is simple attention logic. We form the weights here. We use these to kind of weight these value vectors. We add them up, and we form via these two weights and via basically these two value vectors, we form this vector here, and we just repeat the procedure for all of the output vectors. So that's basically the main contribution of the paper. Everything else is about trying this new Perceiver.io model on various different tasks. And I'm gonna just cover a single one, and that's the language, like the glue benchmark. And they compare with BERT base. And you can see here, depending whether they use tokenization, so sentence piece is like a famous tokenization algorithm, or simply using UTF-8 bytes. That means no tokenization at all. You just take the raw text and you encode the characters as UTF-8 bytes. And so you can see that they kind of report results that are on pair with BERT. But here's a catch. I mean, even though they're kind of making the flops similar here, the number of parameters is obviously way bigger for perceiver I/O. So if that's something you care about, this is obviously not going to be like a fair comparison, right? And I guess this is where perceiver I/O shines. The reason is when we have UTF-8, the input size is going to be way larger, and then because of that, you have to kind of reduce the depth of the BERT model, and that means you have less parameters, less expressive model, and you get way bigger gap here. And I find that very cool because just using UTF-8 encoding instead of having to devise these intricate tokenization methods, and tokenization is literally a field in and of itself. So being able to avoid that whole step and still manage to have these results, like even better than using sentence piece, is pretty damn amazing. Having said that, that's it for this video. If you found it useful, share it out with a friend, subscribe to this channel, hit that bell icon, join the Discord community, and until next time, bye bye.